I have three kind of goals in this presentation. I want to talk about an upcoming challenge, discuss one possible way we could consider tackling it, and some ideas that possible solution led me to. So there are many ways to think about Monty. I kind of just want to introduce another lens through which we can view it and chat about it. So here's the problem. For our initial demo, we're basically assuming we know the boundaries of objects. We have an object in an empty void, and we basically get a label that says, are we sensing the object or are we sensing just the void? So that's fine for kind of getting the ball rolling, but it's a challenge that we'll need to solve sometime down the road. And if we can solve it later, then we can fall back on all the stuff we're developing for the initial demo. So these little green things are supposed to represent, a label that says, all right, I'm sensing the Numenta mug, and these red observations are not on the mug. So of course, in reality, the observations would look more like this. You just have, little bits of sensory input, and you don't know what they belong to. So
in terms of, well, it's not as simple as that, but I'll let you keep going. I mean, if you think like, oh, I have this image and I'm trying to process an image, it feels like that. And if you're thinking again in 3 dimensions, whether you're dealing with touch or 3-dimensional vision, then the problem isn't quite like most people think of it.
Well, you will see plenty of examples of that.
Yeah. Okay.
Yeah. So this is the problem I want to solve. So another way to phrase this is that just based on this image that you see here as an example, from just one static image, I can't really tell where one object begins and one ends. I can't reasonably say that these are 2 objects versus one. But using a depth sensor or even a touch sensor, I could reasonably build something that looks like this as a model of my sensory input. And now if we take that real sensory data away and see this from the model eye view, this is what we're left with. So yeah, this is my point. I don't think from just this sensory data, you can know that these are 2 objects and not one. Now, how do we know in reality that they're separate? One way we can do this is if we actually run our finger along the object to start sensing it, you're going to move the object a little bit, and you're going to notice that one object moves and the other one doesn't. And when you see that they move independently of one another, you now have some data that suggests these are 2 objects, not one.
But if I'm moving my finger over this object, I can't move it over both objects at the same time. So the confusion only comes about when I jump from one to the other, right? I mean, or are you assuming I have 2 hands out there and one's touching one, one's touching the other? If I'm just moving my finger over an object, I won't incur the thing. I won't run into it. I won't even know about it. So I don't need to move it, right? If I'm just following the contours of an object with my finger, I wouldn't know about the other object unless I go down to the table and up on the other side.
Yeah, well, so that's what I'm assuming actually, is that like when you sampled the object, you sampled both with your finger because they're touching in the image that I presented.
But this is an image. I'm saying if you're touching, that's not the case, right?
What Jeff's saying, like if you touch this and it moves, you don't know that this happened.
Well,
you're not touching this.
I'm just saying I don't even have to have it move. I'm just saying when I'm touching this like this, as long as I'm doing this, I'm not even touching this one. So I don't even know that it exists until the only way I might do this, I come down on this surface and go over here and then go up on this surface, right?
What I'm trying to say is in this example, there's no space between it. It's like this.
So they're really right next to each other. Like,
they're next to each other.
Because that's not what it looked like in the picture.
Okay, I should have made that clear. The idea is that you don't know if they're glued together or not, but they're contiguous.
They're touching. They're part of the same. Okay. Well, then why do we even think they are separate? Now you're saying, oh well, because one's moving relative to the other one.
That's what I'm saying. Is from just raw sensory data, without seeing the object's behavior, you don't know that they're separate. You could just say that.
Okay, but the image implied that there were like 2 objects on the table, but you're saying they're really sort of glued together in some sense.
Yeah, they're right next to each other.
They're not glued together, they're just touching.
Yeah, but one could argue like the stapler, the top moves relative to the bottom, but I don't think they're separate objects, right? So even that's not sufficient here.
So maybe that's like the second point. You need to understand the behavior of the objects.
Yeah, that is kind of the point that I'm making, is that in the stapler case and also in these two objects right next to each other case, the behavior is
So I'll even challenge you on that on this, because it seems like, you know, when I first start learning things, you know, we don't learn things that are like this. We literally isolate things as much as possible. So that we have no confusion about it. Like I'm teaching you to read letters of the alphabet. I don't show you words. I don't show them. I mean, we show a letter on a white space and there's like, that's it, right? There's nothing other. I don't show two letters butting up against it. So that's the A and this is the B. So in some sense, so the question is, you know, once we've learned those things, there's an inference problem, but that's not the same as saying, oh, these things are right up against each other and I have to learn one from the other. Because inference is different, right? Inference is like, oh, some such sensations I jump out as, oh, I know what that is, but this is not part of it. You know what I'm saying? So I think we have to be careful here. You know, are we talking about inference or learning? Because I don't think we can learn the world very well, especially when you're young, as a series of things all, you know, we need to isolate them.
yeah. Okay, so for this presentation, let's think about you have basically no knowledge of how the world works.
So you haven't learned anything.
You haven't learned anything, or I'm kind of thinking about how we're going to train Monty. And you're right, maybe one way to train it would just be to isolate objects and not deal with this, but
I think that's what, I think that it's almost like have to do that in some sense. I mean, you can have multiple objects around, but your idea that these are actually physically touching each other it makes it difficult, right? Because how do I know that these are not one object?
I mean, that's the challenge that I'm bringing.
Well, I'm saying that maybe it's an unsolvable challenge in terms of learning, and that you just don't want to try to learn the world like this because it's not going to work well.
Okay, well, that may very well be the case. My goal today is to present a way to learn despite this challenge.
Okay.
And I'll see what you think about it. So to me, it seems that if you see that the two objects move independently of one another, that would be a signal that it's two objects and not one. So
With the exception of things like staplers, right? Yeah.
With the exception of things like staplers. This whole presentation, I haven't not yet integrated the idea of object state.
Okay.
But what I kind of think is happening here is that you have a model, this graph model, and it's a bit like a hypothesis. This is how I think the world works. And implicit in having that hypothesis are predictions that your model makes. And you can use actions to test the predictions of your model. So let me run through what I mean.
So again, I'm going to be picky here. If I have a model, it means I've already learned something, right? What have I learned? A moment ago, I said, okay, we're going to assume we learned nothing. We didn't know anything. And now I have to learn a model. And I got these objects touching each other. I'm going to do that. And I said, hey, if you already have models of the world, then it's a different problem.
Yeah, so I don't mean models that you previously stored in memory. I mean, online, I went around and sensed some stuff. And so now I have a model that I'm building up on the fly, but I don't know what it is. I don't know
Okay, so it's not,
what it is.
I wouldn't call it a model. I have a set of observations that, right? A model to me is something you've learned, right? I mean, that's how I use the word. It's like I've learned that, I have a model of the cop, I have a model of these classes. It's not just a set of observations I don't understand yet.
So, okay, but what would you use for the term of, that collection of displacements? So I know the relative.
Well, I have a
positions
set of
things.
observations that I'm
That's
trying to,
just
a set of observations, right? And now my set of observations cannot make predictions because I haven't learned anything from them, right? It's just a set of observations because I haven't learned this in the past. How could it make a prediction about the future?
I mean, you've still learned a graph, a short-term graph.
Well, then you've learned something. I mean, either you've learned something or haven't, right?
Well, then what if that's learning is building a short-term graph, what would you call it when you
Okay.
take a
If
graph
I
and
run
turn
a
it into
short-term
known
graph,
category?
then the only thing I can predict are the observations I just made. Right? I can't predict anything else because if it's not stored, the best I can do is like some sort of temporary memory of like, I've observed this, this, and this, and this. If you want to call that a model, fine, but it can't make predictions about what's next because it hasn't observed it. It doesn't have a bigger model. Typically, I have a model of something and then I observe some subset of it and then I can infer the entire object, right? So in this case, I don't have a model. I just have a set of observations. And I suppose I can make predictions about the observations I just made. If I said, oh, I saw A here and then B here, I can predict A will be back there. But I can't predict what would go over here. I can't predict what's C over here. How could I? There's no model for that.
But even if you see a new object, you can still form hypotheses about that new object and how it will interact with the world.
The new object, if I don't know what it is, and I don't have an object, all I have is an observation, right? All I have is a sense of observation. So again, if I haven't learned anything in the past, I don't know how I can make predictions or have an hypothesis about something.
How about this? I don't know what this object is. I just have this collection of observations, these relative displacements. And the prediction that you could make is that if I pick this thing up and move it, the whole thing is going to move with my hand. It's sort of so simple that it's a little ridiculous, but that is a prediction that you could make with this model, I think.
Okay, I'm sure I go for that.
Okay, so here's what I'm getting to is that when you try that, you're going to see that now you've got two objects instead of one.
Maybe here's my phone with a eraser on top. I pick it up and I move it. So I think
yes, you can construct counterexamples.
Well, that's the point of these arguments, right? Is to probe and probe.
You're right. It's not a foolproof strategy.
Okay.
But it is possible to knock the eraser off the phone still.
Yeah, it is. Okay.
So now I have different sensory input, and I even have that my depth sensor shows there's a gap between these two things. The idea I'm kind of trying to get to is this iterative loop of like building a model. It doesn't have to be of a known object, but it can be instead of model, I'll say gathering a set of observations, predicting how they should behave, and then taking an action to test if my prediction is correct or not, and then using the outcome to update the model or the observations. I don't think anyone is terribly sold on this idea yet, but as a comparison to how we tend to train deep learning, I think it's a pretty interesting alternative. Instead of just training with backprop and doing something like the following, the loop would look more like I take a bunch of actions to sense the world. I store those observations in a buffer of some kind. And then I make predictions and select a new action in order to test my predictions. I actually execute the action and then I update my belief based on that test.
Is there any other action and test that you think would work other than I'm trying to separate these two objects and move one and the other one doesn't move? Are there any other sort of predictions you're thinking about? Or is that it?
I have not thought of others, but I'm guessing this idea would extend to other things.
Okay, I'm trying to understand because select an action, make predictions, those are very generic terms, right? And I was objecting to it because I was saying, well, you really can't make predictions about the world that you haven't learned anything. And then you came up with the example, oh, well, I like to predict that if I'm trying to do separation, if I move one thing, the other thing does the other thing move. I'm like, okay, that works. But it doesn't seem like I don't know if there's a more general version of this. So I'd just be careful because we're using words that sound like there's a model to make predictions. But it's not really a model. I guess the hypothesis is that a bunch of things I sense now that they will, if they're separate objects, they will be separated and they will be in the same location from each other.
Another example of a possible action would be you could squeeze something. Okay, squeeze this.
Yeah, but what does it tell me?
It tells me these observations I had, they're flexible and everything.
Yeah, but does that tell me when we're trying to figure ground separation or object separation? What do you learn from that?
Yeah, not in terms of objects,
Okay.
but in terms of understanding that this could possibly be.
All right, I'm just working on Ben's hypothesis.
Well, I mean, if you squeeze it, everything that moves along with it is part of the same, could be part of the same object. They're connected. I guess that's a little bit like your.
But yeah, that would be similar though to the idea that it's the behaviors of objects that you need in order. It's not just like what the object is; it's how it behaves. So you can kind of like you don't know the language coffee cup for this thing. But you could still learn how it behaves and assign a label to it in your own kind of language and know how it works.
I think you can't. To know how it works, you need a model, right? You just got to have a model. I mean, in some sense, you're arguing we can take a temporary model by assuming a bunch of observations are all together. And then if one moves and the other one doesn't, then the assumption is that they're not all together. That's pretty much the gist of what you're saying. But it's not a general purpose prediction, right? I can't predict how any of these is gonna, I can't predict what the other side of this coffee cup is gonna look like. I can't predict what, other things. Because I just don't have any prior knowledge about it. I just have, what you're saying is I got this current knowledge of just one viewpoint and I haven't built up any other stuff.
Yeah, I would maybe just think in terms of not predicting parts of the object you hadn't seen before, but I would think about predicting behaviors of objects.
But again, what other behaviors could there be other than, object behaviors have to be learned too, right? That's part of the models. So I'm not dissing it. I'm just saying one thing you pointed out is it's not like behavior of the object. Moving the object is not a behavior of the object. It's just like, hey, if I move this thing and something else doesn't move, then I might assume that it's separate. But it's not really a behavior of the phone that I moved it. It's just, I don't know what to call it, but it's not really, oh, phones don't move like that. It's like, I can move anything. It really is. It's a more point solution to this problem, which is not making it bad. I'm just saying it's a point solution problem, which is if you move something and other things don't move, you could make an assumption that subset of the graph is separate from the other ones.
That's exactly what I have so far. I think you might be right. It could just be a point solution, but the problem of occlusions and knowing where objects begin and end is still a pretty big problem. So even a point solution to that, I think it would still be.
I see occlusion sliding back in the image, thinking about images, right? If you think about, again, the alternate to this, I'm not saying this is wrong. I'm saying the alternate is I start off by learning about the world by continually moving my sensors over the object, whether it's my eyes tracing something or my fingers tracing something. And as long as the objects are relatively isolated, like I pick this up in my hand and I do this, I'm not going to get confused where the boundaries of this thing are, right? I'm just not. And I can learn this model really well. And now when I see it in a scene with something else I've learned really well, it's a different problem. It's not, now I have the ability to say, oh, these set of displacements belong to a cup. These are displacements, if I start focusing on them, they look like a phone. And they're not the same thing. I already learned models for these two things. And so the figure ground separation problem, as it's stated typically, is assuming you don't have a model. All you have is some sensory data and you're trying to figure out where one thing begins and where the other one doesn't. But if you do have a model, then it's easier, much easier. Because I just do this displacement and say, oh, that's a cup and this is the phone, and I just see them as separate things.
Maybe interesting question here is, how does the model first come about?
I just give an example. You pick something up and you touch it and you move it and you lose your eyes over it, right? You don't.
Was it a sufficient amount of exploration?
Yeah, right. But you're not doing it in a cluttered scene, right? Yeah. I don't try to teach you what the letters of the alphabet look like by showing you a paragraph of text.
I would still say that fits squarely into this, because one of the points I'm trying to make is that you can't just sit back and passively observe, images and actually decisively say how objects will behave or where one object begins.
Right.
By actually picking it up and manipulating it and sensing it.
But then my argument, then you build the model, right? And so you start with the model, then the separation becomes easy. But the way you started the process and thinking about this, you're saying, hey, I have this image and I can't tell where one is and one isn't because I don't know anything. I haven't learned a model yet. So there's a big distinction. Do I have models of these objects or do I not? And
well, if I don't have a model yet, am I still allowed to pick up an object and manipulate it?
Of course you can. You can grab something even though you don't know what it is, and you can touch it, or you can reach your hand in the black box and run your fingers over this, or you can look at it. Of course, that's how you learn.
It is part of the exploration, like what you say. I explore this, I pick it up, and in the process it falls apart, and I start to.
Well,
once it's automatically isolated, sufficient amount of exploration.
Yeah.
I mean, maybe you could say if you already have models of other objects, you could generalize behaviors of objects to new objects that you don't have a model of yet. So if you don't know about any objects in the world yet, this might not work. But if you already know that they are solid objects that you can pick up and manipulate in certain ways, and then you see a completely new object, you can apply those behaviors to that new object.
Right,
Well, you
right.
don't have a model yet.
But that's not a figure ground separation problem, right? That's a generalization of behavior problem. I mean, Ben started off with saying, how do I tell where one thing begins, one thing ends? So and I think
Yeah,
what
I
you
think
said didn't make sense, but it's a different problem, I think, right?
yeah, I mean, I feel like this is a more general framework than just for figure background separation. I mean, it's a pretty generic, general framework that you can use to solve a lot of different problems.
Yeah, right. I agree. Totally. I mean, that's the whole model building we've been talking about, right? That's not new. I'm just reacting to what Ben said, which he started off by talking about we have no knowledge and we're presented with something about in the world and how do we determine where one big thing begins and one thing ends, right? That was the question you posed.
That's where I started.
Yeah.
And but one of the other things was just, adding a different way of looking at Monty, the stuff you've already laid out. And so some of this is going to seem very obvious, like the idea that you pick up objects and sense them to build the model in the first place.
Yeah.
That's not new. I'm saying that I'm kind of proposing this loop here as a different way of thinking about it. You sense data to generate hypotheses, you take actions to test them.
Okay, and then so that to me is sort of the whole model building exercise here, right? If I open that up to the more general scenario, where I say I have models of things in the world, and I pick things up and I act on them, I make predictions. That's what the model's all about, right?
Yeah.
And every time you do any movement, you're testing it, not explicitly, you're not saying like, I need to test this, but anytime you do anything, the model predicts what you're going to get. And if it doesn't get it, then you know something's wrong. So that is the framework of learning in the thousand brain theory, I guess, or a quarter column theory, right? So I agree with that. I'm not sure now if that's new or not. That seems like what we've been saying all along.
Yeah. So now I'm gonna, in the next slides, I'll take this stuff, which is not new,
Okay.
and I'll just add a little bit of spin.
Okay.
But Lucas, do you have something?
Yeah, I was just gonna say maybe that's not a good comparison because what you have in the right is exactly the training loop for model-based reinforcement learning. That would be the most direct comparison. And it has deep learning has nothing to do with it, but model-based RL is just that you laid out there.
Okay.
So I think that was true for any model building system, I think, right? Anything that has a structural, three-dimensional sort of like model.
That involves action selection, right? That involves a power.
Well, it basically involves the idea that your sensors are moving relative to the object. That's how I think of it. I'm not sure if it works in the enforcement way, but if you're moving your sensors and your actuators relative to the object, then you're going to make predictions. The model will make predictions, and then it'll test it automatically. It's just nature of the.
Yeah, and even on a higher level, we know from child psychology that children actively generate hypotheses and test them about new objects. And they are, working like little scientists, basically, when they see a new object, experimenting, and they don't just randomly interact with it to figure out stuff. They actively test different hypotheses and then very efficiently figure out how objects work.
Well, I agree with that. Do you have a specific example in mind when you think about that, Vivian?
Yeah, for example, there were these studies, they made this machine, I forgot how they call it, like, and then they had like little blocks that had different colors. I think they called them blurbs or whatever. And then the children would figure out which colored blocks activate the machine in what combinations and which don't. And then if they would glue two blocks together, they would have to like do some kind of combinations of them to turn them around. I can send some papers on that.
I'm just curious what kind of, I just didn't know.
Yeah, it's like a machine that lights up and produces some noise when you put different colored blocks on it.
But you're saying when they show them a new version of it, they've used previous learning to try to figure out if it works the same or if it works differently.
Yeah, exactly.
Yeah.
Okay, to briefly respond to your point, Lucas, my comparison here is not really to bash deep learning or say there's no example of deep learning that incorporates these ideas. It's more just to say this feels like a cool idea, actually. The idea of like going around and building models of objects that feels very different from like couch potato image classification where you just feed the model lots of examples. So
Oh, yeah, I'm gonna
the
feel
idea of
bad.
kind of an embodied learning
Yeah.
situation.
Maybe on the left, it
How
should be
would
more
work.
like feed forward, pure feed forward processing versus an interactive. Sense that would be a better comparison.
Yeah, I just point out that what's on the right is not really new, so.
Well, it's certainly not new for us, right? This is the core of Monty, I would.
Not even for like the community, so I
Yeah.
mean, like this, the idea on the right as well, just what model based are out of.
Do those model based RLs, do they have actions and sensors moving and things like that?
Yeah,
Okay.
yeah. That's exactly how.
Okay, now thinking about actions, I wanted to try and just talk about the advantages and disadvantages of getting to choose actions. First, the disadvantages. It's complicated and we don't yet have a whole theory about how actions are generated and executed in the brain. And so if we put a lot of effort into solving action selection, this could be a complicated or expensive task for us. And Jeff, a couple of weeks ago, you pointed out the possibility that we may be able to be successful in our first application without introducing that complexity. So
Well,
it's
again,
possible we can
actions
bypass it.
are, I put them on a spectrum. A simple spectrum is your actions, you're just tracing the outlines of something. It's an action, right? You're just following things. Another action would be saliency, right? You are looking at something, your eyes move towards something that's a little different. Those are pretty basic actions. And then there's the actions like, oh, if this really is a coffee cup, I should be able to unscrew this lid. Let me try that. That's a wholly different scale of, that's like model-based selection. The first two examples I gave really weren't model-based.
Right, and I took this a bit out of context. You were referring specifically to object manipulation when you said this, so.
I was saying you could build a useful system that worked on the first type of action selection, which is not really model-based. It's, the model tells you what to expect, but the model isn't driving the actions. The model isn't saying, here's what to do to achieve some goal. Like, again, think of this. The idea that I might think this is a coffee cup, therefore I predict this top should come off. Therefore, if it doesn't pop right up, maybe it should screw up. Those are really high-level motor-based things. There's nothing to indicate there's a screw on this, nothing. Yet previous knowledge about how things work says it either should pop off or should screw off. And if not, then I'd say it's not a coffee cup. Whereas just like, oh, I just picked this thing up and I'm learning what it is, and I move my finger around it and learn a model of it, that, and then I can predict where it is and so on. That doesn't require a model to learn. Those actions don't require a model. So, when I was saying earlier, we might be able to do systems that aren't capable of like, oh, let's unscrew the top type of thing, right? But they still with movements, and movements are actions. You move your eyes, that's an action. Whether the cortex is controlling or something else doesn't really matter. Does that make sense? You're looking at me like
I'm just kind of parsing it because there's a couple parts. There's a spectrum of actions, and then I'm thinking about what distinguishes Monty from other things. One part is that it's a model building, obviously model-based reinforcement learning.
it's a model building
Similar,
system
right?
and built on moving sensors, which there aren't many. So the right, most of the machine learning isn't like that.
Exactly.
That's the number one thing. And then how the models are, how the models learn and how sensors get integrated is other components of it. And ultimately, we have the idea of the ability of taking actions that are very sophisticated, like seeing the generality between objects on screen top. So there's a spectrum there of things, right?
Okay. Well, yeah, this presentation is clearly lacking some nuance with respect to
No, I just
types of actions and the
Well,
levels of complexity.
I think that's a general idea, even in neuroscience, that there are movements of the body that are top-down generated, and there are movements that are bottom-up generated, and both have to be handled properly.
Okay. Some possible advantages of being able to include actions, and I guess here maybe we'll think about going beyond just being able to move my sensor, like move my eyes left and right, but thinking about being able to interact with objects. It provides a much, okay, so first of all, speed. In the example I gave earlier, if you're just kind of receiving images of objects, you have to just wait around until you see an example of, two objects that are next to each other from an angle from which you can tell that they're not the same thing. And until you get that, you don't know. If you get to actually manipulate objects, you learn this immediately. I think that was sort of your point, Jeff, initially, that,
Yeah.
well, yeah, if I can just pick it up, I just learn instantly what this object is. So speed of learning is increased, I think, by being able to interact with objects. And if we run with this hypothesis testing loop idea, it's possible you can get in touch with the world faster by kind of quickly testing hypotheses. It also might lead to better generalization. So you might, by interacting with things, you might learn their behaviors. And just point out that Judy et al. Has this levels of reasoning hierarchy and suggests that you can't go beyond level 1 without being able to interact with objects. So there are clearly advantages of being able to manipulate objects.
What is level 1?
Associative reasoning. Levels 2 and 3 are interventions, and then level 3 is causation.
So again, I just want to be really clear on the first pro one there. Everything in mind is built on the idea of actions for learning faster, right? I mean, that's the entire premise of the thing. So I assume what you mean here is more top-down interactions, model-based interactions, or I mean, nothing in Monty happens unless you move your sensors, right? That's the way it works.
Yeah, I was thinking more about actions like manipulations and things like picking up objects. It still would seem like it would be really hard if all I had was, a camera that I could move around the room or something, but I can't actually touch these objects or move them.
Well, I think obviously you can touch them. I think let's make a couple of distinctions here. I mean, one is like we talked about, oh, there's an object out there and I can touch it with my finger in different positions, or I can look at it in different positions. The next step is, oh, I now lift this thing up. I'm holding it in my hand and now moving around. That to me is a subtle difference from the first one. It's not really substantively different. It's you're still basically just moving your sensors around an object, but instead of moving around the object, you're holding it and changing its orientation to you. And I think it's a little bit more complex, but that's still in this category of I'm learning what the morphology of this object and what it looks and feels like by just sensing it, right? And whether it's stationary or I pick it up, it's really not that much different. Then the other thing is
There's a
again,
difference, like you could pick up an egg is different than pick it up like a lead ball.
well, you'll learn something by picking it up, right? Yeah, but my point is this object here. If I was restrict you to learning by moving your finger around it like this, or I'm holding my hand and move my finger like this, and while I'm doing it, I'm changing the angle to me. That's a more complex kinematics problem, but it's the same. You're basically learning the same way. You're learning what sensations occur at different positions relative to the object, right? You just have to translate it to different orientations. But that's, I'm pointing out is that is a very small step from just having a stationary here. But when you start, that doesn't require really it doesn't really require having a model of this object to learn it. I can just start learning the model by moving my sensors over it and feeling what it is, and I build up this model. But now there's a separate question here is if I've already learned models of other objects and now I see a novel one, how do I generalize to the previous thing I learned? And that in some cases, well, even just something, how do I even learn that this thing has a removable top? That's a different type of model we have to solve. Like the model is not a static object, but it has behaviors. And now if I have behaviors, how do I apply it to novel things that might have similar behaviors? That's a whole different level of manipulation and action. Again, those are top-down cognitive cortical action generation versus the just touching, moving your finger around is much less so.
Okay, so I'm hearing you. There's a big difference between unscrewing the lid or pulling off the lid type of action.
Or seeing the commonality between a new object and an old object.
Okay.
Right. That requires a model.
It's almost like there's a separation between like a semantic model and a behavioral model. But even the distinction that you were pulling together of feeling around it when it's static and then lifting it up, you actually are learning more about it. You're learning more about the heft, the volume.
Yeah, but it's a
agree.
modest difference. It really is.
But that would be enough to identify
Maybe, but let's not focus on that corner case of, oh, this is really heavy and therefore it's surprising. Just imagine it's this cup and there's no surprise about its heft. I don't think we should focus on that corner case. You know, I can pick it up and maybe it falls apart. I mean, yes, I could learn something by doing that.
Well, it aids in identification, separation.
Yeah, but let's assume there's nothing like that. It's just this object that's sitting here and move my fingers around, or I pick it up and I move my fingers around, or I turn it like this, as opposed to walking around. Those are very qualitatively the same.
Right, but I'm not trying to make a distinction. I'm not arguing with the distinction between the behavioral model we're talking about, which requires previous experience and recognition of where the similarities are. So, yeah, there's, and I don't know whether that goes, that those 3 levels of reasoning, whether that fits in cleanly to those 3 levels or not.
I don't think so. Well, I could, when I've looked at it in the past, I didn't see how it worked, but maybe it does. Maybe someone can make that argument.
I'm not sure what the intervention is.
Okay, I want to, now that I've gotten feedback from everyone, I want to frame the way the rest of this presentation should be interpreted, because I was actually anticipating that you would be hesitant to have all the object manipulation types of actions included right away. And I was going to be in favor of including all the object manipulation kinds of actions.
Well, okay, but the way you phrase it here is so open-ended and generic that it fits what we're doing right now, right? Actions, faster learning, active learning, hypothesis testing. That essentially is the static object moving your finger over that describes Monty. So I think if you're arguing more for, we want to use previous models of objects to make hypotheses about the behaviors of new objects, like cognitive action selection, model-based action selection, right? Where the models are determining what to do based on some goal or some active hypothesis testing. Then okay, I'm interested in that, right? I just think the language here is it's
Okay.
too loose. This describes exactly what we're doing already. So,
Well, I'm what can I say? I'm in favor of what we're doing
Okay,
already. So
okay.
I was actually trying to be balanced, but I'm really on the pro side here.
Were you thinking about more inference at this point, or?
Still training though. Like you should, exactly like Jeff said, you should be able to acquire your first model of an object by like reaching out and touching stuff and manipulating it.
It's got hypothesis testing in this. So you already imply, or do you also imply you've previously trained models?
No, I don't think so. Can I go on? Because
Yeah,
sure, go on.
I want to get to just like this. I don't think this presentation has as much merit as I was hoping, which is fine.
Okay,
But
sorry.
there's one kernel of an idea that I do want to still get some
let's-
feedback on. Okay, so
what's the word? I can't read it.
yeah, so I was asking myself, what are the benefits of being able to like manipulate objects and everything? And can we get some of those benefits if we just have like sensors and we're allowed to just change the orientation of the sensor? And what that led me to think is, well, the 2 things that you can play with if you want to do better in that situation are the prediction and prediction error components of your model. So here are 4 ways you might structure predicting your next sensory input. The first would be kind of a brute force approach. Oh wait. I'm sorry, this slide is supposed to be hidden.
Oh, we're cheating.
Yeah, let me go to the next. This is a draft slide. Okay.
mouse pointed back to
Okay, brute force. Okay.
Okay, so yeah, the first one's supposed to be this brute force approach. This is what you kind of might do with deep learning often. It's like I have an observation, I have an action, and I'm going to use that to predict what my next sensory input is going to be.
Based on what? Based on,
The observation and the action, that's all you get.
so it's just a pairing. So it's just saying, I've learned this pairing. if there's no underlying model, is that what you're saying?
Well, that's a model, right? That what Ben's called.
Well, it's a very
predictor.
simplified model.
It
It's-
is a model. but-
Okay, it's like the stupidest model ever. It's like, it's like saying, okay, fine. There's no underlying three-dimensional structure to this model. It's
But
just
this is commonly used
okay, fine,
out there in
fine.
deep learning.
Yeah.
So I'm just adding layers of structure to it. So the next step is I take my collection of observations and displacements and I put them into a graph. And then I take the graph and then an action and I predict my next sensory input.
Yes, that's what we've been doing so far.
So now it occurred to me that like you could take this even further and say, actually, I'm going to predict what my model will be at the next step. So I take in a graph and an action. And instead of predicting my sensory input, I basically predict in terms of the graph and the displacements of these observations in the environment. So I basically predict, I move this thing over. I predict this kind of mesh object moved over. And from this, I could try and learn the mapping from the state of that object in the world back to the sensory input and now compare the sensory inputs. And then the even more extreme version would be, I predict my graph, I get sensory input, and I actually construct a graph from the new sensory input, and I only do the comparison, the error, in terms of the models, not actually the raw sensory inputs.
I'm lost on that one.
So let me,
Okay, can we just leave that text up for a minute? I want to read it more carefully.
Okay.
So even you're using predicted graph model, there's a whole bunch of assumptions in what you're saying there, Ben. You say I have a graph, which means I have a model of the object, right? That's what a graph is. It's a model, right?
Okay, can we say just a collection of displacements?
Okay, but that's a model. That's what it is.
Okay, but it's like a model without necessarily a label yet.
Okay. But a graph is defining a structure of something.
Okay, so
So,
we call
and
it a
that-
model then.
But it's a new, you haven't seen this object yet.
oh, is that right?
That's kind of what I'm thinking. I just have.
I thought you said the graph plus action equals new graph as opposed to, but I assume the first graph is something you've already learned.
I was thinking of that graph is what you got from your sensory input from like going around and sensing.
This is our short-term graph.
Short-term graph.
Got it.
That's good language.
Then you say predictor number 2. It's just a graph.
What would you distinguish? How do you distinguish predictor 1 and 2?
So I'll get.
So 1 is it's just the same as number 2 using a graph model, but you also move it.
So maybe one way I'm thinking about it right now, maybe this is wrong, is I have this cylinder and I'm constructing a graph of the cylinder. So I have some expectation of what I'm going to see, and I know about cylinders already, so I have some expectation. Now I hit this handle, and now, oh, it's not a cylinder anymore. Now I can predict this entire shape of this thing, so that's another graph in some sense that I'm
Okay.
predicting.
that's-
Is that what you're
that's what
thinking
Ben's-
of, or?
No,
I
don't
was
think that's what
no,
Ben's
I was more thinking of like you have this you have a short-term memory graph of an object in the environment, and I predict that, for example, if I apply a force to it sideways, I'm going to predict that my new graph is going to be
But why
basically the
is
same
it-
thing.
I
but
mean,
in a new
then you're-
But the
location in
graph
the
doesn't
environment.
change.
Yeah, right. The graph doesn't change unless
Because
you're.
the graph is an object-centric coordinate, so that graph doesn't change when you move it.
Yeah, I
think that may be different.
Yeah, I was assuming that kind of get to know something about where it is in, I guess you could try and say it's in relation to the body.
So that would be a new pose in relative to the body of that same graph.
So that,
The
yeah.
graph itself doesn't change, but it has a pose relative to.
That's
the body.
correct. I should have, I was
Yeah.
running at the last minute to make these slides. It should, you're right, exactly, just say same graph, but new pose relative to the
Okay,
body.
okay.
All right, well, that's a really important distinction because we didn't create a new graph at all. We just moved an existing one and fine, it's a new pose to the body, but it really isn't a new graph. And I'm not even, I guess you could say that there might be a prediction about that. If I say just place everything right someone out, then I can predict how these things are in the place. But it's almost trivial. You really haven't learned anything from that, right?
I don't know if it's trivial or if it's a subtle point, because
What have I learned by moving some unknown thing to some other
It's a
position?
rigid body that isn't before.
Okay, fine, fine.
what I'm
that's pretty
saying
good.
though is that it's a different way of making predictions. Instead of making predictions by just going from graph and action to sensory input, I'm now going from like graph and action to new pose of the graph to body, and then from that to sensory input.
Yeah, but it's in some sense, you haven't learned anything new at all. I mean, Kevin says you learned that it's a rigid object, fine. But other than that, if I see a set of things in some arrangement, I don't have no model for it, I have no expectations, there's no additional knowledge I have, it's just some temporary thing. And now I move it to another place, and now it's a different pose relative to my body. I haven't really learned anything. What have I learned other than it's rigid, right?
Well, okay, actually, I want to even make another distinction. You're not executing the action yet. You're predicting what's going to happen when you take.
Okay,
the
so
action.
yeah, I make a prediction, and then the prediction comes true. What have I learned?
Wouldn't it also depend on the background, like what's behind it?
Fine, well, now you can go back to the original premise Ben put up there, like figure ground separation type of problems, right? But I'm not sure if we're still trying to solve that, or you're making a broader point about models here. I think Ben's trying to make a bigger point than just like, how do I separate one object from another?
Yeah, this is a bigger point. This is an idea about different ways to structure prediction and error.
Okay, I'm going to argue that there's nothing gained in this particular model version here.
Top right version.
Yeah.
How about the bottom right?
Well, let's
version?
talk about the bottom right. So what I have a graph, which is again a new graph novel. I've never learned this, right? So this is a new time I presented this thing.
Yeah, and it again replaced like the stuff on the right, the predicted graph with just graph in new pose relative to my body.
Okay, so let me put it in the body. So I move the object.
Mentally, you haven't actually moved it yet. You're
Okay.
just predicting what it will be after you.
Okay,
action.
then what's my new graph? Build model.
That function should also take the graph, right? You're updating the model given a graph and then your observation. That makes sense.
But there's no update of the graph because the graph hasn't changed. As I said, just because you moved it doesn't mean that the relative positions of things haven't changed. So the graph itself hasn't really changed at all. There's no new, it's still the same set of components.
Are you moving the graph or the sensors in that sense?
You're moving the object.
But you have a different perspective, different sensations.
Well, he didn't say that. I mean, he didn't say he moved the object and flipped it over so I see the backside of it. I don't need to move. I mean, that's a different type of thing. It's like, oh, well, here I have a model of this film, but I don't know what the back or side looks like. I can rotate and see that and rotate and see that. I can learn more.
Have new observations in there. The new observations for me, it's a new sensations.
But he didn't say that. He just said move the object. So I'm not sure if Ben is meaning that. If I just take this cup and I don't change its orientation of my body, if I just move it someplace, and now I'm observing it over here, I haven't learned anything new.
Well, you were saying from a different angle, so it had me.
But well, have I changed the angle of the object to me, or if I just moved it? That's a big distinction. If I have this thing here and I move it over here, I'm not saying anything new about it. There's no new information to be had by it. There's no way I can learn anything new about it just because it moved over here, other than this Kevin points out about together.
So
If I rotate it, but then I can just rotate it right here. I don't need to rotate it over here. I mean, yes, I'll learn new things if I do this. Absolutely. I'll learn new things if I do that.
let me try and clear this up because the slides are not the clearest, I admit. What I mean is I have this short-term memory model of the object. I choose an action. I don't execute it yet, but I'm going to predict where the object is going to be relative to me. So now it's over here. And now let's pretend while it's in this new location, I do a bunch of observations and I sample what it looks like here and I build a graph.
But why would the graph be different when it's there than the graph over there?
Yeah, so that I don't know that really has any merit, but the next slide has a visual
Okay.
of what I was talking about.
Okay.
And it's possible it still actually will, because I still think this idea is kind of cool, even if it,
Well, I'm trying to tease apart what you're actually going to learn from doing this. Now, again, if you're trying to do the figure ground separation issue, I agree that you could learn something from that. Right.
Okay.
So we're going back to that. Okay.
basically, yeah, the idea was to cast error prediction error, not in terms of my actual sensory input, but in terms of two models. So this might be the model that I got from a bunch of observations while the object was in one pose. I predict that if I, grab it by the handle and move it over, the whole thing should move over to this new coordinate. What I observe is that, in fact, this stays here and this moves. And now I take a bunch of observations of this.
Of both of them.
Yeah. And build a separate short-term graph
Of the two things.
of the two things. And now I compare my observed model, basically what I actually see after I take the action, from the predicted model. And so I have to learn that this stuff in red, I predicted this would be here and it wasn't. And meanwhile, this I didn't predict would be here and it is. So I have to learn the correspondence between those two. And I can actually also go back and take my initial observation, and with this new model, I can explain the error and basically correct
But
what I did wrong.
isn't the only thing you can learn here is that these are two separate objects that don't move together? Is there anything else I can learn about that? It doesn't seem it's more generic than that. It just seems like that's the only thing I can get out of this. It's like, oh, well, these components didn't move when I moved it, and these components did.
Honestly, I haven't thought it all out yet. I was trying to just get some ideas on the table today, but
Yeah.
I did think that this might extend to notions of object state, like the stapler.
Well, that's an interesting idea. But to me, that would be the interesting thing to explore, right? That would be the interesting thing to explore. How you learn models of objects that have different states. So that would be, I think that's a more interesting problem. I have trouble imagining, but that could be just my imagination. How are you going to do that without first learning a model of not just a temporary, contemporary observation, but actually learning a model, something like a stapler?
Yeah, maybe for a stapler case, you have a bunch, like again, you mentioned a bunch of observations all around the object. And you do a bunch of manipulations, and essentially you learn as a constraint how all those observations move, right? Because the stapler, like this is a hinge.
Yeah. How you do that in a model, like a graph model, is hard to, I've been thinking about it, it's tricky, right? I have an idea how to go about it, but it's really hard.
Well, if you're doing more than just moving the object, if you're applying forces to it, and all of a sudden the stapler snaps open, like to say,
Yeah.
So you're toying with it to see what it could do.
Yeah, right. But how do you actually represent that in the model is challenging, right?
Well, I mean, that's kind of the hope here, is that you learn the the difference between two models. Like I snap it open, I basically build a new model, and then I do the model diff. So instead of the red cylinder that was here and there, I learned that like this part of the stapler that's wide open corresponds to the part that was closed a second ago.
But in this case, they don't correspond, right? Right here, you have two cylinders, they're not corresponding, they're totally different things. You don't want to learn them as the same. In this example on the board, and they're projected, right? That's how you posed it, right? The back cylinder is not part of the front cylinder.
Correct.
So you don't want to learn that as behavior of the two cylinder object. That's not what it is.
So I'm
But
gonna push back a little bit.
Okay.
In a very general sense, there are two solutions to this. You could say it is one object, it has the behavior that these two parts move completely independently.
Well, then they can't be completely independent, because then it wouldn't be one object, right? Unless they're somehow,
I'm
quantum
saying
linked.
That's what I'm saying though, is learning that it's one object with this behavior of total independence is equivalent to learning that it's two objects. The way the objects will behave in those two models will be the same, I think.
I don't get it. I'm missing it. It's fundamentally different. A stapler is one thing, and it has a constrained set of states it can be in. And I learn it as one thing, and I have to learn what those states are, and I have to learn how their states transition from each other. It's all part of one model of stapler. Here I have two separate objects that can move completely independently in the world. They're not one thing. and otherwise they say everything in the world is, causally tied to everything else, which can't be. So here it's a totally different thing. Here I'm saying basically say this isn't one thing. These are two separate things, and I can't build a model of them, a single model of them, because they're two separate things.
Jeff, really, I agree with you, but what I'm trying to do is use the same type of thinking to explain object states and boundaries between objects. And so by learning that there's no physical connection between these two things, by learning that they behave and move independently of one another, that inference to me, like,
Okay, again, I see this as a way of separating two objects. It's a way of saying I can differentiate these observations into two, object A and object B. I agree with that. But I'm having trouble extending it beyond.
I mean, I don't know that we're gonna make progress until I think about it some more. So
Sure.
I think it's fair to say,
If what you're saying is the sensorial impression you get, there could be two potential hypotheses. They're connected but are not. And so if I care about it, do I want to take an action to distinguish that? Then I move on from there. So you don't necessarily, if the sensor is giving you, the sight sensor in this case, giving you ambiguous information and you want to tease it apart, you have to take an action to do that. Otherwise, it still remains unresolved. So it's part of explaining what it is in front of me and how the composition of what I'm seeing is.
I agree with that. That's right.
Right.
That's the object separation problem.
Right. So, but that's the thing, is that in the light of sensor ambiguity, you have to take some action to resolve it. Once you've done that, you know how to classify it, and then you can move on from there and learn more interesting things about it. But it's still a case where if you're presented with something that's, from a sensor's point of view, a conundrum, you would like to be able to resolve that. Because otherwise it's ambiguous. You don't know if it's connected or not.
Right, but that's a very sort of point problem. And this is a solution to that problem.
He's trying to present a simple example.
Yeah, but again, it's a problem of object separation as opposed to where I'm trouble is how does this extend to learning object behaviors in a model?
I think that's a different thing.
Right, that's my point. That's why this is a point solution. It doesn't, Ben said he thinks this is a way of getting to the latter one, the other one, but which is really a hard problem. So I'm just making that distinction. I'm pushing back on the idea that this is a general way of learning object behaviors.
If the set of actions limit that you have is to move an object, that's all you can learn.
No, even if
No.
I can push it, I can do anything.
No, I'm right. Okay, but the point of it is saying that there are more complex things to try to tease out the behavior of the thing. You apply
Right,
forces to it.
Right,
So with those more, that increased richness of actions you can do, you can learn more.
yeah, but I don't, and under these set of premises, I'm arguing you can't. These set of premises are that I do not have a model of the object yet. All I have is a temporary constellation of features. I haven't learned anything yet, and that I can, and that's the fundamental issue I'm having. This idea is that you can't really. I have to learn a model of the object before I can make predictions about behaviors of that object, right? This is a trivial behavior. I move it from here to here. It's really the object hasn't changed. There is no behavior of the object. That's just moving something from one location to the other. The hard part is how do I build a model of this thing when it's actually doing things, deforming or unscrewing and things like that. That I don't see can be done. I think you have to start with a model, that structured model to do that. You can't just do it. You can't learn behaviors of something that you haven't learned.
what I would like to do is, go ahead.
Go ahead. I wanted to riff on something you presented earlier, which I thought was interesting.
Okay, I mean, basically, Jeff, I've taken your points to heart. I still feel this faint intuition that I might be able to get somewhere with this. So what I'd like to do is go back to the drawing board and see if I can make this idea work.
So what do you think
subject
the
to
core of the idea is?
Well, there's one core thing you presented that I liked. I wanted to riff on a little bit. It may not be exactly the same thing, but you were about to say.
I have a point, like just lies back.
Okay, maybe it's the same. I don't know. But what
Do
I
you want me to go back to a different slide?
No, it's okay. I think one thing I like is the idea that what we're doing is predicting graphs from which we predict sensations rather than predict sensations directly. And I thought that was, I think there's some interesting directions to take
I
that.
do
Yeah.
appreciate that.
And I don't know, maybe we've thought about that before, but it's sort of a very crisp, clear way of stating the thing. And
Yeah.
the way I'm
It's the first step on a hierarchy of abstraction, I would say.
It could be, yeah, but I'm thinking like, suppose you start sensing, some shape, right? And we built up a set of displacements in a graph. And in our experience, we have a whole bunch of different models that we've learned in the past, right? And now we're sensing here. And we can immediately, all of us here can start predicting that there's actually a completion here. There's some sort of, based on everything we've learned in the past, there's like a graph, a way of filling out this graph that we can already predict. And then we can start sensing it, but maybe now we start sensing it going this way. Okay, now it's not this graph anymore. Now everyone can probably predict something. I don't know what. I
Is
might
it a
predict this one.
is it a prediction of a graph, or is it an illumination of possibilities?
Yeah, maybe it could be a union of graphs.
Right,
Yeah.
so then you're not really predicting the graph, you're basically in this.
It's a union of things, but you're not necessarily predicting a sensation directly, which seems harder. Predicting maybe a union of graphs or a specific graph based on everything you know, it seems like a little more tractable.
Well, it's a subtle language thing.
It's a subtle language, but it seems more tractable algorithmically to me.
Well,
I
right,
think
so
it's
I-
more than just language. I think it's, like you said.
I just thought that was
I
an
don't know,
interesting
I don't-
distinction. Again, I don't know if this has legs
It's a
or not,
prediction,
but,
so I like that idea too, but I thought of it completely different. To me, this is just narrowing down the union of possibilities. I have some data, evidence of what I
no,
have.
I think it's more than that because it may be that, let's say you learned about cars, now you're seeing a toy car.
Yeah,
That's a little bit different. It's distorted a little bit. So it's not exactly predicting a union of things you've seen before, but it's specific
but
to what you've seen today.
but do I see it as a car? If I see it as a car, then I've inferred it to a previous graph, whether it's different or not.
Oh, no, yeah, I'm assuming you're using previous graphs to do this.
Okay, so.
But it's specific, it's sort of molded to the observations.
So what
you're
is the
seeing now.
new model I'm predicting in that case?
Either this graph or union of graphs.
I think it's conceptual, the fact that there's continuity object. That's.
I'm saying more than that. It's more the shape based on what you've seen before. You can predict different shape, but it has to, the scale and deformations has to fit what you've seen already. So that's the slight distinction.
So it's funny because you say if it's a toy car, but I've recognized it as a car, so I've already mapped it to a graph. That's by definition, otherwise I wouldn't see it as a car. And now I'm making, maybe I'm making novel predictions based on the fact that it's a toy car versus a real car.
Yeah, and it's smaller, it's it
But
may be
am I
more
predicting,
stretched out.
but am I predicting a graph, or am I saying, here are some attributes, I have a model of a car and this one's different, and I'm able to extend those, somehow those, it's like scale, just take scale. It's small, it's not a real car, it's small. So I somehow have to be able to scale my model.
Yeah, so it's to me,
Is that
my
predicting?
riff on this is that we're actually predicting a new graph.
I see,
But that has smaller displacements. now.
well, I wouldn't think that, because it seems to me that just to infer that it's a car to begin with, I had to use an existing graph and somehow recognize it independent of scale. I had to say, I already recognize it's a car that's small.
Yeah,
And so it's not
but
like,
then in order to be able to predict the sensations, you're not necessarily using the previous car at a different scale
why not?
because this is a new object now. You are building a new model.
Okay,
It's
but
not my, Lamborghini that I
Okay,
don't
I
have in
guess-
my driveway.
I guess it's interesting.
It's this one.
It's interesting to say, are you predicting a new graph, or are you basically saying, I have an existing graph of cars. I now realize this one is small and different in other ways. I'm now going to create a new graph, which has these different attributes. So I can, and now I'll recognize it as a toy car.
Yeah, because that.
But am I predicting a graph, or I'm just creating a new one that's similar to the old one and doing a twist
Well,
on
these
it?
are, these are predictions because you haven't sensed.
Yeah, but they're
Yeah,
being,
it's
they're
sensitive.
predictions based on what my previous model of
Yeah.
cars was.
Yeah,
So I'm not sure I'm predicting a graph, I'm still making sensory
it's a
predictions.
graph because I can predict,
I'm
you know,
predicting,
new sensations
Yeah.
and new displacements.
right, but it's not a new, am I predicting a graph or new sensations of displacement?
I'm just
I'm
proposing
saying
that
that-
we predict a graph instead of the
Yeah,
raw
I'm saying you're predicting
sensations.
the entire graph from which you can predict sensations.
Exactly.
It's a subtle distinction.
I think it's, yeah, but it's, I'm not
You're sort of
buying it.
instantiating the whole thing.
And that's not,
Because now you can tell me, oh, what would it be here? What would it be there? It's like you're predicting the whole structure.
I guess to predicting a graph, it's sort of in a sense
Maybe
that,
instantiating. a new
yeah, it's
graph.
instantiating a graph, right? It's, I mean, to predict something, I already have to know what it is.
Yeah,
right?
maybe instead, but we haven't sensed it yet.
Oh, fine, that's all right, I got it, but it's, I'm not predicting something, I can't predict a graph I've never learned before. That's impossible. So,
Here's kind of a flip side of this. Here's one reason I don't think it's just about predicting sensory input. You don't really notice like blinks in your visual stream. You don't notice the small microsaccades your eyes are always making.
you don't even notice the big saccades.
You don't notice pixaccades, fine. So I think there are lots of examples how the brain sort of filters sensory input. And so I don't know that it's really comparing like to like a predicted sensory input to like an actual input. It may actually be kind of comparing like what I think the world should look like to like the new model that I have of the world.
But in the
next
end,
step.
the only way you can test your predictions is by sensory input. There is no other way to do it, right? There is no other way to test it. So you're gonna, in the end, you're gonna get sensory input and it's gonna run against a sensory prediction. I could predict a graph, that's like hallucination, right? I'm predicting a graph and I don't bother checking it with reality. And I can just imagine in my head, oh, that's all good, great, right? But I'm not really testing it.
Yeah, maybe instantiating a graph is a better word, but you know, it's not anything you've seen before, but it's using information you've seen before. You can kind of impute a new structure.
Yeah, but it's gotta, so what I've been thinking about is it has to, there's some core components of the old graph that have to be transformed to the new graph.
Yeah.
And that is some attributes of the displacement that are still gonna result.
But it could be something completely bizarre, you know, like I could say it's a horse with the head of a man.
Yeah,
Right? Like, and maybe you've never seen it, what it's
Yes.
called before. But I can still construct the graph in my head of what, and I can make predictions about it. So it's a new thing. It's not anything, it's not a subtle change of what you've seen before. You're just.
well, that's a good
constructing
example. That's a good example of I wouldn't even call it predicting a graph. I
Yeah,
would
and
say.
predicting is not the right word.
That's,
Yeah,
that's what I'm focusing on. I think you can instantiate a new graph by combining two previous ones.
Yeah.
I could make a graph that actually has my cell phone attached to this coffee cup. If it was really glued there and I pick them up and all right, that's the new thing. It's like, okay, I'll learn to live with it. Right, but I'm not, I just
Yeah,
don't
so I
like.
think this idea of sort of instantiating new graphs completely, or a union of graphs, I thought that was kind of an interesting
Okay.
take, and it's very, to me, it's very, you could imagine writing code for that. It's very clear.
Okay. So I agree with that. I think that's one of the problems our graph modeling has to solve, right? You have to be able to create new instances. I've made that example before, like you can see a coffee cup that's a different shape, you still need a coffee cup, but now you can remember that one uniquely. Or I see a cat that's like other cats, this is a unique version. I need to be able to create a graph of that unique one somehow that's different than the other ones.
Can I run with this hallucination idea for a second?
Yeah.
If we think we have stored lots of models of objects, like I have a model of everyone in this room, and you know, maybe somebody like gets up to leave the room. I could start predicting. I'm not predicting sensory input per se. I'm just predicting the location of Jeff is going to be close to the door in a minute, as an example. That is basically a hallucination, but
Yeah.
I'm kind of wondering, maybe that's actually what's happening, and you don't bother correcting it until you collide with corrective information.
Of course, how
Until-
could you? How could you correct it until you, there's no other way to do it, right? Yes, we can hypothesize about future things that haven't happened. But,
Like, I'm wondering if like you actually, what you're experiencing is basically the hallucination at
well,
all times until until the prediction isn't correct, and then you kind of have to like. readjust.
Of course, I think that's right. I mean, how else could it
So
be?
then that is like predicting,
But none of it's real until you've tested it, right? You can't,
Yeah, it's a hypothesis.
it's just like, okay, I'm imagining that I would sense this if it's actually true, but I haven't sensed it yet. It'd be like saying, I'm imagining that when I reach down under this chair, I'm gonna feel these levers, right? Well, until I reach down there, I won't know that, but I imagine it. I don't think that, it doesn't teach me anything. I haven't learned anything yet until I actually reach down there and see, oh, what does it feel like? Are these levers there or not? So I think that's what the models that you do then, they let you run through scenarios and imagine what would happen if you did this and if you did that. I'm just arguing you're not learning it from that. Well, you're not validating your model. You're just testing, you're running through hypotheses and say, well, this could happen, that could happen, but I haven't really updated my models yet.
yeah, but now the idea that I'm proposing doesn't have to do with utility. It's just an interesting idea that like what you actually experience is kind of in the model world, and it's often in the model world, and it's only kind of in the sensory world when you pay attention to your sensory input specifically, or when your sensory input is not consistent.
I
with the
just
model.
totally, I agree with that 100%. That is, I agree with 100%, right? It's no different than me saying like, well, I'm imagining that there's a mental logo on my coffee cup here, and I'm going to assume it's correct until I, rotate the cup and I don't see it, then I know it's wrong. But have I learned anything? It's just basically a model makes predictions. Until you sense them, then they're just predictions.
Yeah, you live in your hypothesized world.
Right.
And until you get evidence, it's just otherwise. I did an experiment like with virtual reality classes. I first took a 360 picture of one room, so they can like look around the room and experience it. And I went to a different room, looked at that room, and it feels like you're actually in that room. And then when you take off,
Where you're in a different room?
yeah, a different room. Let's say room A, I took the picture, I observe it in room B with the glasses. Then I take off.
I'm so confused. I'm sorry, you're in another room, but you're wearing the glasses.
Yeah,
So
So it
are
feels
you
like you're
seeing a
moving.
different room or are you actually seeing the first room?
I'm seeing the first.
Or if you're just wearing glasses, how would you know what room you're in?
Yeah, it feels like you're in the other room, right?
But how else? Yeah, of course.
You take it off and it feels like you're suddenly transported in the other room.
Oh, I see.
It's kind of a weird sensation. It's like,
Yeah.
oh. So you suddenly adjust your sensation of where you
You
are.
travel to some other place and you put it, and all of a sudden you snap back.
Yeah.
So there's whatever path integration you did is being fooled.
Yeah,
Maybe that's it.
it's like
Yeah.
transported. Yeah, but coming back to that, you wanted to more general also.
No.
You wanted to more generalize this thing. So I would put it as a challenge to how can you represent like the degrees of freedom of the object? Like, for example, the state law.
Well, how do you represent its behaviors? Right? Yeah. That's a hard problem we're working on. We proposed a partial solution once and it's not complete. And so that's a hard problem. I don't see how this addresses that problem. That problem, I have to have a model. The model somehow includes the behaviors of the object and the actions which made those behaviors, happen.
I'm
And
still gonna try it though. I'm still gonna go back and see if I can get it to work. So
Okay,
I'm still interested.
If you get a solution to that problem.
But you also have objects that are not physically attached to each other. For example, the switch and the light.
Well, that's true.
That's kind of eerie.
well, that's interesting.
There's no attachment there. There's a cable somewhere, we know that. Otherwise,
It feels like you don't perceive it as one object, right?
we do, I know, if
I don't imagine these two things in some constellation to each other in some position and say, oh, there's this one thing here, right?
But I control the behavior.
It's more like if I do this button here, there's causal relation to some other behavior elsewhere. It doesn't feel the same as a stapler open and close,
Does not.
but it might be, but it doesn't feel that way.
Yeah, maybe it's just more.
I'm gonna excuse myself in
Okay.
10 minutes, I have to do something.
Yeah, sure.
Um,
It's just broadly under the like causal relationship, which is generally temporal prediction.
Yeah.
To do this.
Yeah, it's probably why, small children have fascination when there's a causal relationship that is outside their physical bounds, and they flip a switch and they see something happen, and they'll sit there and flip it for quite a while, just, it's like magic. The fact that I can have this.
They do that, by the way, I'll tell you right now, they'll do that just for spinning something on a rod when they're really young, and it's like magic. They go, look at this, they keep spinning,
Yeah, I mean, something happened.
My granddaughter's doing that right now. It doesn't have to be like switches and lights.
Yeah. Well, I mean, your ambitions grow. So.
No, I think it's interesting. She's learning some sort of action policy about spinning things, right?
Yeah.
Um,
And also the fact that if she does it again, the same behavior is repeated,
Yeah,
opposed to
good.
being random.
Okay, we only have a couple minutes, so I want to hear what Lucas's point was.
Yeah, can you go back? Yeah, yeah, so the brute force approach, when you call predictor, that's actually a model, right? So you have a model, you got observation action, you have next action, and then you use that error to update your model. Right, that's the traditional way. What you're proposing, we do have an error, but that error cannot be used to update the model because you already know how to build the new model. So what's the point of the error? The error will only allow you to update your predictor, but why do you need the predictor?
I was thinking the opposite. The point is that you no longer update the predictor. You do the updates purely in the model space.
But why do you need the error?
But the predictor is the model, right? Is that what you just said?
Well, I thought the graph was the model there,
But
right?
there is no graph in that one.
No, I'm looking at the bottom right.
Oh, I thought you were talking about the brute force one.
Because you already know how to build the new model. So the error is not going to play a role in there, right? That error would be there for the predictor alone, which predicts given modern action, what is the new model.
I hear you. It's the exact opposite of what I had in mind.
But how can you use that error to update the model? You can't.
I mean, it's exactly what's on this slide. You have to learn that the stuff that you didn't predict, which you now see, is the same stuff as stuff that you predicted that you don't see. You have to learn that correspondence.
I have to learn how to parse that sentence.
So you go back, see a little green thing in the far left.
Go back to the one slide. Right. This is actually the step you have to take, right? You already have the observed graph, so you know what your new graph is like. So why do I need this?
What is this?
Yeah, I see your error here, but why? What do you need?
It's explain. You have two observations. You have the first observation from which you made the prediction, and then you have the next observation.
Right.
All right. Now I basically use both observations and update so that I have one model for both observations.
Right.
That's what this error is supposed to be for.
Right, but what are you going to use it for?
Instead of predicted graph and observed graph, from this I derive unified graph that explains both observations. Maybe error is not the right term from it, but like replace this line with unified model of both observations. Would you accept that?
I don't know. We can talk about it later. I don't want to.
Okay. Oh, I mean, you might be right. It might just be, it might actually not be doing anything.
Yeah, we can. Yeah, let's. We have to think about more, but we can talk about it. I don't see. I just don't see like formally what is it. I can scribble some equation in the whiteboard and we can figure it out.
Okay.
Yeah, thanks, man.
Thanks.
Yeah, I
everyone.
appreciate-
Thank you very much for all the.
Despite all the
discussion.
acrimonious conversation, it's good to do these things and it's good to argue with each other. So.
No, I really enjoyed it.
Away.
Absolutely.